Okay, I would like to go over the test review for chemical bonding or ionic and covalent bonding. We're not having a test over it, but I would like to give you some type of resource to study because there will be, like I told you in class, some of these questions, the topics in the midterm, so sprinkled all in. So I want to still give you a review so that you can use it as you're preparing for the midterm. So we're just going to go ahead and get started. This is mostly vocabulary, but again, it is multiple choice. It is a multiple choice test, so you will see some of questions involving some of these words in the test, so we're going to go over these as well. But on your midterm, you will have multiple choice, not multiple choice, it won't be multiple choice, there will be a non-multiple choice, I can't talk today, I'm sorry, a non-multiple choice question in the back where you're drawing the structures of them and indicating their shapes. I do want to go over that as well because that might help you if you want to participate in the extra credit. Okay, so first it says fill in the answer for that's best. So it says the electrons in an atom's outermost shell are called its valence electrons. We know this. We've known this for a couple of units now. Sodium wants to lose how many electrons to become isoelectronic with neon? And again, I have started the video without having a periodic table, so I will get one. Okay, so it says sodium wants to lose how many to be isoelectronic with neon? So here's neon right here, and sodium is all the way right here. So if it loses one electron, it will be isoelectronic with neon. So where am I? Sodium wants to lose one electron. When magnesium gets the same electron configuration as neon, it has a what charge? So first we need to find magnesium, okay? To become like neon, which is right here, it's going to have to lose 2 electrons to become like neon. So that if you're losing 2 electrons, you're going to have a +2 charge. Okay. A blank covalent bond consists of 2 shared electrons. That's just a single bond. So a single, wow. Sorry, it is literally the day before Christmas break and my brain is gone. Okay. Single covalent bond. The blank says that most atoms want 8 electrons in their outermost shell, and that's the octet rule. Okay, F, in ionic bonding, the 2 ways atoms can get the same configuration as noble gas is by, well, they're either going to gain or lose electrons. In covalent bonding, atoms blank electrons, so they're sharing. Remember, we talked about that. In covalent bonding, they share, and in ionic bonding, they're actually transferring. And again, this is all black and white here in 10th grade chemistry, but that kind of changes as we go, move on into IB chemistry and then into college. Atoms in group 15 will blank 3 electrons to get a -3 charge. We don't even have to look at the periodic table, but in group 15, they're going to gain 3 electrons to get a -3 charge. If you have a -3 charge, you've gained 3 electrons. So, molecules with 15 atoms, like methane, will, molecules with 5 atoms like methane will have a what shape? So remember, we have a central atom and then we have one up here, 2, 3. So here's 1, 2, 3, 4, 5. What is it? 5 atoms. So that's a tetrahedral shape, I believe. Okay. The Vesper theory stands for the, valence shell electron repulsion. I didn't give myself enough room. Theory. Argon and chlorine ion or chloride have the same electron configuration, so they are isoelectronic with each other. Okay. As L iodide has the same electron configuration as the noble gas what? So iodide with a -1 charge, so if it gains an electron, it'll have the same configuration as xenon. Blank is the only noble gas with 2 valence electrons. So remember, these have 8 valence electrons, which is what all of these strive to have. However, helium only has spots for 2 electrons in that first orbital. So it only has room for, where's the question? Blank is the only noble gas with 2 valence electrons. So that's helium. And why am I writing neon? Helium. Ionic compounds are made up of blank, which are very large structures consisting of alternating positive and negative ions. So this is that structure that I tried to draw on the board. This right here, it's something Jai Ho has made for us. It's I actually don't have it near me, but these are crystals. Okay, remember on the video I showed you guys the crystals. But here they are again. These are crystals, many of them, and that's what we're talking about here. This is just ions that are alternating their positive and negative charge. Okay, when atoms lose electrons, they get a what charge? All right, guys, we should know this like in our sleep by now. When nitrogen bonds covalently, it will make a total of blank bonds. So nitrogen and nitrogen, nitrogen is here. It has 5 valence electrons. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's going to bond here, here, and here. So it'll have 1, 2, and 3 bonds. So it'll have a total of 3 bonds. Okay. Ionic compounds will not conduct an electric current in the blank state, and that's the solid state. So this guy is not going to conduct electricity until it's in its aqueous state. Remember, that's dissolved in water. Okay, moving on. Metals are, where are we? Metals are blank, which means they can be hammered into different shapes. This one is what got you guys a long time ago. This is malleable. Malleable and ductile come back here. All right, blank is the only element in group 1 to bond covalently. So here, remember, ionic bonds are made of metals and nonmetals. However, this isn't a metal. So this is hydrogen, which is the only element here that will bond in covalent bonds. So this is hydrogen. Molecules with a trigonal pyramidal shape have a total of blank atoms in the molecule. So remember trigonal bipyramidal. Trigonal. That's that. Oh, yeah, that's the weird one, I think. I have a total of trigonal bipyramidal 1. There's that center atom, and there's 1, 2, 3, 4, 5. Okay, this is that weird one with either chlorine or fluorine on the ends and usually a phosphorus in the middle, or it's usually one of these two in the middle, something that has 5 electrons on the outside and then bonded with something that has only 1 electron on the outside. So that's going to have 1, 2, 3, 4, 5, 6 atoms. Okay, trigonal bipyramidal is that weird shape one. The difference between trigonoplanar and pyramid shapes is that the blank shape has an unshared pair of electrons on the central atom. So pyramid is like here. Okay, you have 3 atoms connected at the bottom and a lone pair at the top. What's the other one? Trigonoplanar. That's this one. Okay. This is trigonoplanar, this is pyramid, so unshared pair of electrons. So that's this one, the pyramid. Okay, a double covalent bond consists of how many shared electrons? So a double bond, here's a double covalent bond. We know that there are 4 electrons here, but make sure you don't get trolled. Sometimes on the test it says pair of electrons, and sometimes it just says electrons. So make sure you're reading that type of question correctly. In this case, it doesn't say pair of, so we're going to say 4 shared electrons. If it said consists of blank shared pairs of electrons, then you would say 2. The 2 types of bonding are blank and blank, ionic and covalent. In a blank covalent bond, electrons are shared unequally. So this is polar, when there's a more negative side to a molecule. Okay. To write the electron configuration for potassium. So potassium is here. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, okay? So I'm just going to go ahead and write it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So that is the electron configuration for potassium. Write the electron dot structure for potassium. So we write the letter for potassium, and then on the valence electrons is on the outer shell, which is the highest number. Sorry. And it has 1 electron here. So that would be your Lewis dot structure. Okay, so how many electrons will potassium gain or lose? It will lose this 1. It's easier to lose 1 electron than to try to gain 7. What charge will potassium have when it loses or gains? It will have a +1 because it will be short 1 electron. Write the new electron configuration. So it'll be basically isoelectronic with a noble gas, 2s2, 2p6, 3s2, 3p6, 4, whoops, we stopped there. Okay. What noble gas is potassium now isoelectronic with? So we have potassium here, and then it's going to be isoelectronic with argon. Okay. Write the electron dot configuration for nitrogen. Nitrogen is 1s2, 2s2, 2p3. The electron dot structure would be 1, 2, 3. How many electrons will it gain or lose? It's going to lose these 3. 1 and 2. So we have 5. My bad. Okay, so 5 electrons. How many will it lose or gain? It's going to gain 3. It's easier to gain 3 than to get rid of 5. So it'll have how many electrons will it will gain 3. What charge will it have? A -3 charge if it gains 3 negatives. And write the new electron configuration for nitrogen. So 1s2, 2s2, 2p6 if it's going to gain 3 electrons. And what is it now isoelectronic with? That will be neon. If potassium and nitrogen bonded together, what would the formula be? So we have potassium and nitrogen. Okay, so we will send this here. Nitrogen, whoops, we need more potassium, sorry. Here. So the formula would be K3N. Okay, number 5. Draw the structural formula for each of the following molecules and indicate if it is polar or nonpolar. So remember what, sorry. Okay, so if we have 1 C and 4 H's, so 1 carbon, 4 hydrogens, I like to look at which one needs the most bonds, and I like to put that in the middle. Hydrogen needs 1 bond, and carbon needs 4 bonds because it has 4 valence electrons, and it's missing, it needs 8, and so it's missing 4, so it needs 4 bonds. Hydrogen has 1 valence electron. It's missing 1 because the maximum is 2, because it's that 1s shell with only 2 electrons that can fit, like we mentioned here. So carbon will go in the middle. So carbon here with 1, 2, 3, 4 valence electrons, and I should have given myself more room. But we'll put an H on each side. And each H will have an electron, and then they will pair. They'll share those electrons, and the bonds will look like this. Okay, and then, let's see, it wants us to indicate if it's polar or nonpolar. So since there is a central atom with no lone pair of electrons, we have all hydrogens here, so it's going to be nonpolar. It's going to be nonpolar because these are all everything connected to that central atom is the same, and there are no lone pairs, which means there are no like electrons like that. Just ignore that. Okay. Okay, moving on. Basically 2 bromines. So there's nothing going to be really in the middle. You have 2 bromines. They each have 7 valence electrons. So let's draw it and see what it'll look like. So you can draw them just side by side. I like to draw the vacancy in between them so that we're not drawing some weird circle going around. So 7 valence electrons, 6, 7. 1, 2, 3, 4, 5, 6, 7. And these 2 will share the middle electrons. So the molecule will actually look like this, 4, 5, 6, 3, 4, 5, 6, and you will have a line here, and this line represents 2 electrons, so this one will have its 2 electrons and this one will have its 2. And since this is an even molecule, there's no uneven sharing of electrons. These are both the same atom, therefore the electrons will be shared equally, so this one is also nonpolar. Okay, IF. So I is located here, which has 7 valence electrons, and F is also in group 17, which has 7 valence electrons. All of these do. So basically it's going to look similar to this, except 2 different atoms, which might give you, oops, I am getting ahead of myself, sorry. I'm sure you can already predict what will happen, but just in case. Okay, so iodine has 7, 2, 3, 4, 5, 6, 7. Again, I like to leave the vacancy in the middle. It's not like you're going to be counted off if you don't have it in the middle. It's just more easy when you're drawing this circle. So they're going to share these 2 middle electrons, making the molecule look like this, I. Okay, so that's what it'll look like here. And it's going to, instead of being nonpolar, these two have two different electronegativities. So if you remember, electronegativity increases as you go to the right and up. So this has a higher electronegativity than this does. So the electrons will kind of go towards this way. It'll be, they'll be pulled this way because fluorine is more electronegative. So this one will be polar. Okay. We have Si, S2. So Si is here, and it has 4 valence electrons, so it needs 4 bonds. S2, so sulfur, has 6 valence electrons, so it needs 2. So silicon needs to be in the middle, and these two will be on the outside. So silicon in the middle, and sulfur on each side. So remember we said silicon needed 4 valence electrons. And on the test, make sure I know the difference. I know that that's a dot on the I and not an electron. Okay, sulfur had 6 electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And sharing will look, one will go here, a bond will be made here, a bond will be made here, and a bond will be made here. So that means there's a double bond on this side and a double bond on this side. So it'll have Si, SS, and silicon has 6 oh, I'm sorry, I forgot my other bonds. Silicon had 6, but now it has these 2 in addition. So it'll look like this. Okay, so there's 1, 2. Remember, this will repel these out a little bit. Okay, this one has 8 electrons already, 2, 4, 6, 8. So this one's good. 2, 4, 6, 8, 2, 4, 6, 8. So this is silicon. There's no lone pairs of electrons on the central atom, and each of the atom on the connected to the central atom is the same. So we're going to consider this nonpolar. Okay, antimony and 3 iodines. So we have antimony here, which has 5 valence electrons, and then iodine, which has 7. So antimony needs 5, 6, 7, 3 more bonds, and iodine needs only 1 bond. So antimony is going to be in the middle. And we'll have an iodine, we'll have 3 iodines surrounding it. Okay, so iodine has 7, 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6. I always just leave the vacant spot next to the where it's going to bond. That's just my preference. Antimony has 5, so 1, 2, 3, 4, 5. Okay, so you're going to have this one bonding with this bonding with this electron, and this electron bonding with this one. I don't like the way I drew that, but it's okay. So you'll have SB, you'll have iodine up here with 1 bond, iodine here with another bond, and we also have this lone pair, so a lone pair. So this lone pair will actually push this, these 2 out, and then we have a pyramid shape. Do you remember the pyramid shape? Let me redraw it up here. SB with 2 electrons, and you have 3 iodines. Okay, and then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then antimony 2, 4, 6, 8. So everybody has their 8 electrons, valence electrons. And this is a pyramid structure. So anytime you have a pyramid structure, it's going to be polar. Thanks to these guys right here, it's going to be an uneven distribution of electrons. So don't be trolled by the fact that these are the same thing connected to the middle the central atom, you do still need to consider these, and consider these basically as just a different type of atom. They're not, obviously, but when we're thinking of polarity, just assume this is something different that's connected to it. They have a different electronegativity, obviously. Okay, so SeCl2. So Se, if you'll notice, everything we're doing is right here in this part of the periodic table, except sometimes hydrogen. And that's because we're only dealing with covalent bonding. And remember, that is only between nonmetals. So keep that in mind as as I'm asking you on the test. To illustrate covalent bonding or ionic bonding, because ionic bonding is where you circle something and tell me where the electron is being transferred to, whereas covalent bonding, what we're doing here, they're sharing electrons. That's when you have that line, that bond between them. Oh, let's continue. Se has 6 valence electrons, and what was the other one? Chlorine has 7. Okay, so Se will be in the middle because it needs more bonds than chlorine. It needs 2 bonds to get its 8 valence electrons, and this one will need 1 bond to get its valence electrons. So again, Se will be in the middle, and you'll have a chlorine on each side. Chlorines have 7 valence electrons. And Se had 6. 2, 3, 4, 5, 6. Oops, I almost forgot the 7th one. So the bonding will take place here. I'm going to write this over here. So we'll have more room. So we have Se with 2 lone pairs of electrons, okay? And then we have, so these electrons will push these chlorines down. I wish I had more room. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's what it'll look like. It's obviously polar because we have this and this. So we will consider this polar. Just don't forget that these 2 electrons, lone pairs of electrons, will be on top, pushing these down. That's it. Moving on, draw the structural formula for the following molecules and indicate their shape. So we're basically doing it up here. With same thing up here, except instead of indicating polarity, we're going to just talk about its shape. So SCl2. S has 6 valence electrons, Cl has 1. So S will be in the middle. And oops, I keep getting ahead of myself, I'm sorry. S has 6. 1, 2, 3, 4, 5, 6. Cl has 7, we know this. You guys will even start to memorize these just like you memorize the atomic masses, which you said you wouldn't. Okay, so there will obviously be a bond here and a bond here. So 2 single bonds. So basically it's going to look just like this, okay? And if you'll notice, you have selenium and sulfur in the same group. So the molecule will also look the same. And this is the same type of, what's it called, shape as your water molecules. And it's called bent. And just, wow, that's an N. And just for fun, we'll go ahead and indicate that it's polar. Okay? It's polar because of these 2, and these 2, it's bent because they are pushing down the chlorine atoms. Okay, Hi, so hydrogen's all the way over here. Iodine is right here. So iodine has 7 valence electrons, hydrogen has 1. So hydrogen has 1, iodine has 7. A bond here, so it'll be H, I, J, K, L, M, N, O, P. Okay, That's how the molecule would look. The shape is linear. It's just straight across. It's not bent or anything. Linear. And it is very polar. Hydrogen is not very polar. I'm sorry. Hydrogen is not very electronegative. And whereas iodine here is more electronegative than hydrogen, but not the most electronegative. So electrons will be kind of attracted towards the iodine side, so it's definitely polar. Okay, moving on. Se and F. So we have Se, which needs, it has 6 valence electrons, so it needs 2 more bonds to be to have its 8 valence electrons. What else? N and F. F needs 1, N needs 3. So we'll have N, since N needs 3, Se needs 2, and F needs 1. N will be in the middle, and these two will be on opposite ends. So N will be in the middle, has 1, 2, 3, 4, 5. Let's make these a little more obvious. Okay, and we have Se. It doesn't matter what side you put them on, because this molecule could be, these aren't like paper molecules. They're 3D shapes, and they're floating around in space, so they're not, it doesn't matter. This could be flipped backwards. Okay, Se had 6 valence electrons, so 1, 2, 3, 4, 5, 6. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And the bonds will happen here, and here, and here. So what the molecule will look like is you'll have an Se. There's 1 and 2 bonds between nitrogen. And there's only 1 bond between nitrogen and fluorine. We'll draw our extra electrons. Oops. Okay, I'm sorry. My phone stopped recording. Cortland called me in the middle of explaining. So I see about where I left off, but I am not going to redo this, but I will explain quickly. So the selenium, nitrogen, and fluorine, it'll create a bent shape because of this lone pair will push these 2 atoms down. So it will be bent, and because of this lone pair, it's going to be polar. Then I went on to do this problem. I'm just glad I didn't do the whole page without realizing that it wasn't recording. So we did COS. Carbon needs 4 bonds to have its 8 valence electrons because it has 4 valence electrons. It needs 4 more to have 8. And so that's why we chose for it to be in the middle. Oxygen and sulfur both have 6 valence electrons, so they both need 2 more bonds to have 8 valence electrons. So it turns out that these two both had double bonds in between. This has no lone pairs of electrons, which makes you think maybe it is nonpolar. But then we realized that oxygen and sulfur, they have different electronegativities. So anytime there are 2 different atoms connected to a central atom, they will have they will always be polar because they have different electronegativities. So we decided this was linear and polar. Sorry about that. Yeah. Anyways, okay, moving on. PBr3. So we have phosphorus here, which needs, it has 5 valence electrons, 5, so we would go 3, 4, 5, 6, 7, 8. So this has 5 valence electrons, and so it needs 3 bonds. Bromine has 7 valence electrons, so it only needs 1 more electron to be have a full valence shell. So phosphorus will be in the middle with 3 bromines attached. And you can start to kind of guess what shape it's going to be. I know that I will have a phosphorus up here, and I know I'm going to have 3 bromines, okay? And it's not going to be tetrahedral because you only have 3 things connected to the central atom. I kind of have an idea. If not, it's no big deal to put 2 on each side and 1 down here, and you'll realize it eventually. Okay, so phosphorus has 5 valence electrons. So 1, 2, 3, 4, 5. Bromine has 7. 1, 2, 3, 4, 5, 6. Oh, I did it again. Okay, so there we go. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so basically there will be a bond here, there will be a bond here, and there will be a bond here. So your molecule and the lone pair will stay a lone pair, so you know for sure it's going to be a pyramid, and you know it's going to be polar, because all pyramids are polar. So you have a phosphorus with a lone pair up here, so we know it's polar. And then you'll have 3 bonds with bromine, and don't forget the valence electrons. You will not get credit unless you indicate the valence electrons and where they are on the test. Okay, so this is a pyramid shape, and it is polar. Si, S2. So we have silicon here, which has 4 valence electrons, so it needs 4 more to have 8, so 4 more bonds. And then sulfur has 6 valence electrons, so it needs 2 more. So silicon will be in the middle and sulfurs will be on the outside. Like that. And we're going to do their valence electrons. 1, 2, 5, 6. Silicon had 4. 1, 2, 3, 4, 5, 6. So there will be a bond here. There will be a bond here. There will be a bond here and a bond here. So basically it'll be silicon with no valence electrons, okay? There will be double bonds on each side, so there's no valence electrons, and sulfurs on each side. So you have 2 lone pairs on these sulfurs. So the molecule will look like this, which is linear. So, which also looks like this one, except it's also linear, but this one was polar because these 2 connected to the central atom are different, so that made it polar. Here, the 2 atoms connected to the central atom are the same, so they're going to be nonpolar. There will be an equal pull on the electrons, so we consider it nonpolar. Okay. The last shape is quite easy to identify, whether you're looking at just the formula or you're looking at the shape. If you ever have 5 things connected to one thing, it's going to be that weird last shape that we learned. So let's go for it and just look at how to set this up. So you have SB, and then you have F. So SB is antimony right here. It has 5 valence electrons, so it needs 3 more. And what is it connected to? F has 7 valence electrons, so it only needs 1. So this is that weird exception where SB is not actually going to create 3 bonds, it's going to create 5. So, and it only works for those that are in this row, okay? It won't work with any other atoms. So SB has 5. 1, 2, 3, 4, 5. And then because I know about what the shape will look like, I'm just going to make it easier on myself. That's 6, 7. Every fluorine has 7 valence electrons. 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So here's how the I guess I'll say it, the trigonal bipyramidal works. You have a bond here, you have a bond here, you will have a bond here, you'll have a bond here and here. You may want to say, but miss, this center atom will have more than 8 valence electrons, which breaks all the rules you've ever taught us. That's okay. This is just one of those exceptions that experimentally works. Yes, it has an expanded octet. It will have 2, 4, 6, 8, 10 electrons, but it just works. So we will call the molecule will look like this. Keep in mind it's not perfect with the paper. Keep in mind that it will, it's 3D, so it's not all flat in the paper, like this one's sticking out, this one's going backwards. Valence electrons. Okay, so that's what this would look like, and the shape of it is trigonal bipyramidal, and it is always nonpolar. It'll always be the same things connected to it, at least in 10th grade.